This is a lecture by Adrian on patterns of glacier retreat for the Royal Holloway Geography for Schools lecture series. In this lecture we will consider why we should be studying glaciers in the present day and also why we should be interested in one specific aspect of their behaviour, which is their retreat. Why is it important for us to understand this aspect of the glacial system in the present day? We will also give examples of how we record glacier retreat in the recent past and extend these surveys beyond the invention of airborne and satellite imagery, which are commonly used in the present day for monitoring glacier extents. Finally, we will also examine a glacier retreat record and think about what might have caused the changes that can be observed. The image that you see in this particular slide is taken from some fieldwork that we undertook in Patagonia, South America, a few years ago. The retreat of the ice can be observed in this image in several ways. In the foreground, we can see the debris-laden ice melting to form small lakes, which are dammed by a massive moraine, which is where the photograph is being taken from. And this effectively shows that the ice front is retreating in the present day. However, you can also see evidence of the ice thinning further up valley, as the ice melt reveals bare bedrock and sediment that has been deposited against the valley sides. Modern glacier systems are an important part of the water cycle with global, regional and local scale impacts. Essentially, glaciers act as a store of fresh water as precipitation is converted into ice, and this mass of ice deforms under its own weight to flow down valley as a glacier. However, its conversion to ice means that the release of water is delayed, as it requires the ice to melt for it to be released, for the water to be released. In comparison to how water is transferred through a fluvial system, a glacier system has a more delayed release of water rather than the more instantaneous flood hydrographs of a river system or a river catchment. Furthermore, the meltwater from the glacier tends to be released during the summer season when the temperatures increase, and therefore there's also a seasonal component as to when the peak in water flow occurs. At a global scale, the release of meltwater can control sea level, with warmer global temperatures generally associated with higher sea levels as more glacial ice is melted. In addition, ice loss leads to changes in the albedo of the landmass, with more heat being absorbed by the darker land in comparison to the reflection of heat back into space from the white ice surfaces when the glacier has a greater extent. The release of cool water into the oceans affects the temperature and salinity in such a way as to affect ocean circulation patterns, perhaps causing cooling in areas such as the North Atlantic when there's an increase in glacial melt leading to fresh water being pumped into the oceans. At regional and local scales, the availability of a constant water supply provided by glacial systems is of huge socio-economic importance. Glaciers have been referred to as natural water towers that release water for drinking, agriculture, recreation and tourism. And if this resource is lost, there are potentially significant impacts on an estimated 1.9 billion people that live within glaciated catchments or downstream of glaciers as the main water supply. It should be remembered that whilst glaciers might be considered a benign force, there are significant hazards associated with glaciers, in particular through glacier outburst floods. These are unpredictable releases of glacier meltwater, either directly from water stored at the base of the glacier or stored behind moraine dam lakes. Sometimes the moraines are ice-cored, and when this melts, the ice dam can fail, causing catastrophic floods downstream. So we have an example in the bottom left-hand corner where you can see that the amount of water that's actually dammed behind a frontal moraine can increase as the ice moves back, and therefore there's a greater potential for it to breach the dam that's provided by that frontal moraine. And you're seeing more and more examples in the news recently of glacier outburst floods through moraine dam lakes and their impact on communities that live downstream of these. Consequently, understanding patterns of ice retreat, The amount of water being released and stored in glaciated catchments is really of great importance as we move forward into what is predicted to be a period of warming climates. In this talk, we want to consider glacial retreat, but to do that we really need to remind ourselves of how the glacier as a system works. At its most simple level, we have inputs of water as precipitation through snow, hail and rain, and there are also additional sources of wind-blown snow and avalanching. This creates surface accumulation, and the net accumulation of this tends to occur in the upper reaches of the glaciated catchment. Glacier flow occurs as accumulation of precipitation and the other sources turns to ice as the snow becomes more and more compacted, so that it becomes firn with only about 25% air within it, and then eventually into ice. It is at this point that the ice can deform under its own mass to lower reaches of the catchment, where ablation becomes the dominant control on the amount of ice within the glacier catchment. Ice loss can be driven by temperature as the ice melts, or wind-blown snow is lost, for example. Ice loss can also occur through the carving of icebergs when the ice terminates in water. If accumulation increases and is in excess of ablation, then there will be an increase of volume of ice present in the upper part of the catchment, and this will be transferred to the lower part. The glacier is said to have a positive mass balance and will likely cause the ice mass to advance its frontal position. If, however, there is a period of continuous ablation of the ice, and this is not replaced by an increase in accumulation, it is likely to retreat due to the net loss of ice from the system and is said to have a negative mass balance. This figure is perhaps one of the most recent summaries of the state of the global glacier stock for those systems that are beyond the Antarctic and Greenland ice sheets. Whilst this might look like a complicated diagram, and the detail to a certain extent is not really important, there are a couple of points that I would like to make. You can see that the global cumulative glacier mass change compared to 1961 is nearly 10,000 gigatons of ice. Okay. With 365 gigatons of ice being the equivalent to 1 millimetre of sea level equivalent, that change of or loss of 10,000 gigatons of ice equates to 2.6 centimetres of additional water that's been discharged directly from the glaciers to the sea in the last 60 years. So the sea level has risen by 2.6 centimetres in that time. Since the rate of glacier ice mass loss is currently increasing, the rate of sea level change is also likely to increase. The other point to make here is that the methods of calculating the changes in the amount of ice over this period differ in different parts of the globe. There are geodetic methods, which are the grey shaded areas on the map, and these methods map the surface of the glacier through time. These might be undertaken by in situ surveys from the glacier surface or using airborne surveys or satellite information. Within this particular database, only 9% of the total glacier stock on the globe has been surveyed in this manner. And the results are gained from this 9% of the glacier stock are also extrapolated to other glaciers in those regions. There are also direct glaciological measurements of the glaciers, which amount to a further 1% of the total glacier stock. Okay, and these require point measurements to be made on the glacier surface on an annual or subannual basis. And again, the results from these analyses can be extrapolated to other glaciers within the region. The benefits come from combining the two data sets, and we have around 1 in 10 glaciers in the world which are currently being monitored in detail and with precision. And we can examine those records for the last 60 years. However, if we want to extend the records of glacier change to beyond the last half century or so, we need to be more creative in the evidence that we use. Here we have one of the longest records of glacier frontal positions that's taken from the Mer de Glace in Chamonix, France. What is being mapped or measured is the position of the ice margin on a roughly annual basis. What is interesting is the source of the different historical documents that are used to generate this reconstruction beyond the 20th century, or earlier than the 20th century. So the graph is showing the cumulative length changes of the glacier's frontal position on the y-axis, and the time is on the x-axis. On the right-hand side of the curve, you can see the measurements that have been made directly from the glacier surface, as described previously. And there are a high density of points almost on an annual basis. As you move towards older parts of the record, towards the left of the graph, the density of the sample points decreases, and also the methods of data collection change, perhaps with greater uncertainty in the measurements that are made. So how are these older measurements actually collected? In the bottom panel, you can see that the measurements or direct measurements are the most commonly used. As we look more closely at periods prior to the 20th century, the curve very much relies upon written sources, maps, prints and photographs, and even the odd oil painting. Examples are given on the right-hand side of this slide. With the pictorial evidence, it is very reliant on being able to spot distinctive features in the landscape, and hence this explains the dotted lines with the minimum and maximum extent and an interpolated value that gives the likely position of the ice margin between the minimum and maximum extents. Although this is imprecise in comparison to modern survey methods, it does give a really useful insight into the behaviour of the Mer de Glace over a longer timescale, so over many centuries. And now in certain places, the position of the ice margin will be also observed in the landscape through the deposition of moraines that are preserved. Now these are material that accumulates at the margin of the glacier. Sometimes it can be bulldozed up, sometimes it may be material that is falling off the front of the glacier and accumulates when it's been relatively stable for a number of years at that particular position. Okay, and they're marked, the position of moraines that are well preserved or partly eroded or completely eroded are marked at the top of that particular graph. So in essence, we're able to produce a cumulative length change to be plotted against time. And this reveals that if you're to rely only on the survey of the last 60 years, perhaps using geodetic methods, you may produce an incomplete picture of the state of the glacier when compared to the last or to the previous 4.5 centuries or so. So here we can see from the period 1600 to 1850, the ice in this part of the Alps was more extensive. It built moraines as a result of small re-advances of the ice margin before a major change in the mass balance of the glacier occurred in the late 19th century, where we can see the rapid retreat which as a trend continued throughout the 20th century. Although notwithstanding that, we may also be able to see periods where the ice advanced forward maybe 3 times during the 20th century. Now, some of the detail for this curve can be investigated further through 2 practical exercises that are provided to accompany this talk. There is one set of data from 4 glaciers in Switzerland through the last century, and then there are 2 glaciers from the Chamonix area of France which have longer records. And there's a series of questions associated with those. Ideally, you will look for similarities in the data sets because in essence they're from the same geographic regions, but you may also make some comparisons between the Swiss and French glacier systems. You might want to comment on the evidence for advance and retreat, consider when the glacier was in positive or negative mass balance, and also consider when the highest rates of glacier retreat were occurring. You should evaluate how reliable these data sets actually are in terms of the length of the time series. Considering when these changes are occurring is also important, and I just want to touch on this as the last point of this lecture. So why did the Mer de Glace increase its extent between the 17th and 19th centuries? Well, it's likely to be an effect of the short-lived climatic deterioration known as the Little Ice Age, where temperatures fell by as much as 1.5 degrees centigrade in parts of Europe. You might be familiar with images of ice fairs on the rivers of northern Europe that were common during this particular interval, and it also had quite an important socio-economic impact. Now on the top right hand side we have an example of a temperature curve from the Austrian Alps, and it's actually a measure of summer temperature fluctuations over the last 700 years, and it uses reconstructions that are developed from non-biting midges or chironomids that have a relationship to summer temperature. Now you can see that there's a distinctive period where the temperatures were below the long-term average, with a maximum decrease of 1.5 degrees centigrade. And this happened somewhere between 1540 and 1920. And this covers the period where the ice in France was at or close to its greatest extent. The question that arises out of this is what drives the ice advance during this period. Here we've got evidence that it may be related to summer temperature decreases, which would reduce the amount of ablation that was occurring during the summer period. But it could also be related to an increase in precipitation, or a combination of the two. Now, whilst we have good evidence from the Austrian temperature record to provide part of that climatic data set on summer temperature, we'd also need indicators of past precipitation to fully understand what drives the mass balance to, in this particular instance, to enter a positive state during 1540 through to 1920. The broader question is as to what actually forced the Little Ice Age, and this remains a point of scientific argument. Some argue that there is a reduction in solar activity, meaning that less radiation reaches the Earth's surface and therefore lower global temperatures, whilst others have argued that there was increased volcanic activity that inhibited solar radiation and general global cooling to occur. And it still remains an interesting debate up until this point. So the Mer de Glace can potentially be linked to a relatively short-lived climatic phenomenon known as the Little Ice Age, but this relationship can only really be investigated through the examination of historical documents and making direct measurements of the glacier surface and relating that to older climatic records that can be reconstructed over the same time period. If we are armed with a better understanding of how glaciers will react to human-induced global warming, it might be possible to better manage the stored water resources and also predict geohazards. At the same time, understanding how glaciers behaved under a range of different natural climate scenarios is also crucial information when developing models of future climate change. If we go back further in time, then we remove the influence of man-made climate change. We have a laboratory of sorts with a range of natural responses to climate change. For example, the link of fresh water release from glaciers to both sea level change and also circulation will itself have a profound effect on short, medium and long-term climatic changes in different regions of the world. As such, more precise predictions will enable more selected mitigation strategies to be developed, and prediction of geohazard, for example, such as glacier outburst floods, for those communities that live in glaciated catchments. Clearly, we have entered a time of rapid glacier retreat, as we can see from the graphs of the Mer de Glace, and you can evaluate how consistent these signals are within the European Alps through the exercises. But it remains critical that we are able to monitor and measure the state of the global glacier stock into the near future. For the practical exercise, I downloaded data from the World Glacier Monitoring Service and created new graphs for a very select group of glaciers. Now, If you would like the Excel spreadsheet to play with the data and generate rates of retreat or investigate the data in more detail, please do get in contact and I can supply it for you. I have glaciers from Iceland and also New Zealand within that spreadsheet. It's quite a good way of developing your spreadsheet skills, so I can blank out some of the data so you can actually undertake some of the calculations that we use to create the graphs. Alternatively, you can explore the World Glacier Monitoring Service website and select different glaciers using this Esri map, and they will give you graphs for the position of the ice front through the last century or so. This particular image shows glaciers, other glaciers in the Chambly area, including the Mer de Glace, the Argentière and Bosson glaciers. In this slide, I've also included other websites which have interesting information on glacier systems and which supported some of the figures that were in the presentation. So there's things like the USGS website. There's also an interesting pamphlet that's available from the Grid Arundel website, which has an atlas of Andes water resources, including glaciers, and it's quite an interesting take on the socio-economic impact of glaciers and the water resource that it provides. Otherwise, that's the end of this particular presentation. I hope you enjoyed the practical sessions. If you want more information on the Royal Holloway Geography for Schools lecture series, then go to the websites or follow at RHUL Geography.